Hello students, welcome to Devo Curiosity e-learning classes. In this lecture, we are going to learn about concept of resonance or mesomerism. We know that the Lewis structure of a molecule or ion can be used for predicting the structural properties and reactivity of that molecule. Several molecules or ions can be represented by more than one correct Lewis structure. For example, the following two Lewis structures can be written for nitride ion, that is NO2-. In accordance with this structure, the nitride ion should have two different nitrogen-oxygen bonds, one with a single bond and other with a double bond. Experimentally, it has been observed that both nitrogen-oxygen bond lengths are same and their value lies between that of a single and double bond value, that is 122 picometer, which is between 130 and 116 picometer, which are bond lengths on the single and double bond respectively. Any one of this Lewis structure alone do not represent correctly the bonding in NO2- ion. The actual structure is a hybrid of these two Lewis structures. The two Lewis structures are known as resonant forms, resonant contributors, or contributing structures, and are represented by placing a double-headed arrow between them. These contributing structures are hypothetical structure. The actual resonance hybrid structure cannot be represented by a Lewis structure and is shown by placing dashes, which indicates delocalization of negative charge between the two oxygen atoms, like in the given figure. The energy of a resonance hybrid structure is always less compared to energy calculated for any of the hypothetical contributing structures, and this difference in energy is termed as resonance energy. High resonance energy indicates higher degree of delocalization and thus higher stability of the system. Similarly, for the carbonate ion, that is CO3-2-, the contributing structures are represented as follows. Here, the negative charge is delocalized among all the three oxygens. Now, let's understand the rules of writing contributing structures. The first rule is the contributing structures should be correct Lewis structure. In the given example, the structures 1 and 2 are resonance contributing structure, while the structure 3 is not a contributing structure. This is because carbon cannot form 5 covalent bonds. In the next example, we can see that the figure 3 is not a resonance contributing structure because nitrogen cannot form 5 bonds. The second rule, writing different contributing structures involves the movement of electrons only. The nuclei or atoms hold the same position throughout. In the given example, we can see that the structure 3 is not a resonance structure. This is because the position of hydrogen has been changed. The third rule, the number of paired and unpaired electrons should be same in the contributing structure. In the given example, we can see that the structure 3 is not a canonical form. This is because it has an unpaired electron, while the structure 1,3 butadiene does not have any unpaired electrons. The fourth rule, the different resonance forms do contribute towards the real resonance hybrid structure, but not all of them contribute equally. In general, more the number of contributing structure, more stable is the resonance hybrid structure. And the more stable resonance hybrid contributes, the most towards the resonant hybrid structure. Next, we'll understand how to determine the stability of contributing structure. First, the structure with maximum number of covalent bonds are most contributing towards hybrid structure. Here in the example, we can see that the structure 1 is the most stable. This is because it contains more covalent bond than the other. Therefore, it contributes more. The second rule, the structure with formal charges contributes less compared to the neutral structure. As we can see in the example, the structure 1 of vinyl chloride makes a large contribution. This is because it is without charge separation. The third rule, if different structure bears formal charges, then a structure with negative charge on an electronegative atom and a positive charge on an electropositive atom contributes most. As we can see in the given example, in the structure 1, a negative charge is present on the oxygen atom. Therefore, it is more stable than the second structure where the negative charge is present on the carbon atom. This is because oxygen is a more electronegative atom than the carbon. The fourth rule: the structure with similar formal charges on adjacent atoms are least contributing. Here we can see when the two adjacent atoms have same charges, those canonical forms have less contribution. For example, the structure 3 below has negligible contribution. This is because two adjacent nitrogen atoms have positive charges. The fifth rule: the greater the charge separation, more the stability. In the example below, the structure 1 has less charge separation than structure 2. Therefore, the stability of structure 1 is greater.